Hey everybody, so we're now recording the audio. This microphone's pretty decent. Give me a half second. Oh, do please. Did I leave it in my office? Who has a Mac charger that they let me borrow? Because I think that's in my office. It's not in my bag. We need the magnetic Mac charger. 50 points!
I got you.
Oh my God, there's like 50 of them. Only if you do not need it for the moment. If you held up a Mac charger, 50 points. That's your last bit of extra credit. Because it's called Brian's an Idiot. Who wants to come up here and plug me in on this side? Thank you very much, Carolyn. So in this good deal, this is the magnetic one. So if you can tell what's happening right here, so my charger should be in my office. Everyone can tell you Brian's been here since about 7:30 a.m. today, but we're going to get some work done. It is time. So dim there. But this recording should be pretty decent quality. You should be able to hear me, and you should be able to see any sort of R work we do here. And we're going with a brand new computer right here. So as we do when we get brand new computers and we get our studio, we get our R script going. So here's our R script right here. Let's get a bigger font size going. You know, and this is a good little talk about your take-home real quick, because kind of want to mitigate some of the take-home possible issues. Man, my neck is going to be crazy after this. If you're watching the video, I'm just like looking down like this. It'd be cool if this was like screen here. I don't even get to look at you guys. How you guys doing? Good, everyone's good. Okay, cool. Me too. Has anyone had the Apple Red Bull? Apple, what is it? Tastes like an apple martini. Not that I advise alcohol, but that was a interesting Red Bull choice on my part. Red Bull's bad? Yeah, it's probably. I'm fine. He's fine. So we got everything going on. Just checking my stuff. Make sure I didn't leave my cell phone anywhere. But the take home is due when? Sunday night. Do not be late because I'll be setting those grades in. Also tonight we have the activities are due. So I looked, and I think the Tuesday, Thursday class is getting hit more by the activities not being complete. Remember, all activities have been completed. Activity 10 was attendance. Activity 11, 12, 13 are actual things you need to complete. I believe it was activity 12 some people were confused on, because that is the partition one that we did the work in class on. But you can still do it. As long as it doesn't have, were you there, you can do any part of it. If you weren't there, just say no. But make sure to do that, because after tonight I will be entering in those zeros so people can kind of know where they stand in the class. Because your grade will drop if I enter in zeros, especially if you have more zeros. So, you know, be doing that now as I'm just going on and on and on, but be careful, make sure to answer the right questions. Remember, the activity answers are related to the activities. A few people did assignment answers for activities, and that does them wrong. So with that in mind, activities due tonight, take home due Sunday. Do not be late on the take home. I think I said, what, a 50% penalty? Because I have to get those graded. You will get those grades. But I can't have someone being like 4 days later, like, I did it, Brian, can I get 20% or 30%? It's like, no, we need them in. We need to see your grades. The hardest ones on the take-home are 10 and 11. They are difficult. 10 is not a time series model. Some people have been saying to me, my time series isn't working for 10. And I say, does it ask for a time series? And they say, no. And I say, then don't do a time series. Be very careful on exactly what it asks for. If it wants a polytrend on the quantitative, I was going to say quadratic. A polytrend on the quantitative means don't put categoricals into the polytrend. If it wants two variables, it wants two variables, not one. So be careful. It's very exact. Does that make sense? Like almost make it a few different ways. If it's not working one way, don't just keep hitting run on it. Try changing it. I want to give you as much forward momentum as I can on this. Start early. And also, so I could actually, I'll make it right here, right now. Why not? Because let me go back into, oh man, I love that I have to lean. That's great, right? Like, can't see anything. So I'm gonna go in, I'm gonna show you how to make the take home and just get it booted up here. To make the take home, go through Brian's 5,000 announcements and go to this latest one that says take home posted. You want to double click this and copy it. Do not go to the link or else you'll be going to the .r script file. Do not go to it. You will then take that, you'll find where R is, there it is. You'll drop that into R. I'm in a script right now, I'm not in an RMD. RMDs are like your Word files. If you notice up there, it says nothing after it. It's just a .r file. So that's just script. Everything in here is R code. Does that make sense? The difference between a script and an RMD. RMD is like Word/script. RMD, or R is just a script. I can run that right here, and now I can make my final exam. And this is what you should happen. You put in Dr. Ding's lucky number of 6, the other of 8, and the other of 6. There you go. And uh-oh, what happened? Oh, God, of course something happens, right? Why in the world would something happen? Did I not copy-paste the full link? Do what? I ran source, right? Of course something happens, right? Oh, I bet that's it. Install. I bet it tried to access Maddie, 20 points. I bet it's trying to access Red class. Oh, because it's trying to pull the donor package and donors in Red class, right? Boom, can't hit it. There you go. It's just performance anxiety. I can't tonight. Been up since forever. No sleep. And the answer is, I think it all ran. Warning messages, and we have all of our different data right here. You can copy paste this all out of here, and we have it. You see, here's the thing, and I'll say this. I kind of shoot myself in the foot because with my R, I actually have it load all the package instantaneously on my computer. So all my packages are loaded by default. So when I load up R, I don't have to do library ggplot2, library nlme. It actually loads instantaneously. But that means if I'm on another computer, I have to remember install library red class, so I have to do all those things. So obviously the donor package was inside, it was making the Q2 data frame. So without the donor package, it's like, wait, there's no donor package. So if you read the error messages, you can't find it. Once you have done this is a big hint. I'm trying to mitigate a few emails. Do not type data Q2 because data Q2 is to load a data frame Q2. Do we need to do data Q2? Can I annotate on this thing? I wish I could. No, it exists. It's right there for you guys. It's there. It exists. Don't worry. If you've done that, you're not the only person to do that. You could also destroy it if you do some crazy things. You might change the way it looks. Who knows? But be careful. That is not what we're going to do here. We automatically have Q2, and you can check to see if Q2 is in there by running the structure of Q2 and seeing Q2 is in there. Got a lot of integers, numeric stuff, factors, all this good stuff. And this really is a great take-home. And I'm trying to think, I don't think, is Duke here right now? Duke? What's up, Duke? Dr. Seaver came into my office, and what did he put on the capstone that they had to do? They had to do making a blank and a blank. They had to make, and what percent of the students did it incorrectly? 80%. You know what they did? They made a model on their training, and then they made the models on their holdouts. Do you make models on your holdouts? What do you use the holdout for? To test it. So they were making models on their holdouts. That means you might what to the holdout? Right there, overfit. These are keywords. We're already breaking into the knowledge part of tonight. You might overfit if you make your model on a data set. To counteract that, we have holdouts, which are the test. We'll get to some more knowledge here in a moment, but I think this at least shows, it's very nice to know. Look at this, big thing behind me. I think this shows you guys how to get started. Remember, 10 and 11 are the tough ones. I don't think 10 is so bad. I don't think 11 is so bad. You just have to be very exact. Very, 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 very exact. So take your time, start early, talk to each other. Do not send code. That's how you get burned. And I'm literally talking, if you get caught cheating or sending code, you and the other person might get a 0 in the class. So don't do that. Don't send it via any sort of text or group things. Don't send out code. Does that make sense? Like, I'm like warning you, I hate dealing with this. It's like, Merry Christmas, you got an F. We don't want that. We don't want that. So, you know, you guys know what I think is all right. Talking to each other, trying to explain things to each other, that's learning. Sending code is like, here's my work, take it. Don't do that. That doesn't help people. I mean, it helps them, but it's cheating. So anyways, any other questions about the take home before we break into reviewing? Silence. Silence is good in this instance. Let's take a look at some data here. I'll tell you the way I make the take home is I think about the concepts we've covered. I got an email today, a really good email. The email said, do we need to know multiple regression? And the answer is interesting. The answer is yes. But wait, multiple regression was kind of on last test. That's chapter 4. But tell me this much. What does multiple regression mean? What is kind of what a multiple regression is? What's a simple regression? I'll say it again. One predictor. What's a multiple regression? More than one predictor. So when you were doing logistic, you were doing multiple logistic if there's more than one X. When you were doing indicator variables and including a quantitative, you were doing multiple regression. So the ideas behind multiple regression permeate through. The ideas of leverage, which we haven't talked about lately, that'd probably be pretty good to cover right here. Let's pull up a leverage plot because we're going way, way back. It's time to go back. So let's do this. All right, so let's load up. Hey, we got some data sets here. Why not? That helps us. Let's make our good old model. Let's call an LM. Let's open up this Q2 data set, see what we got. Let's make a quantitative model to start. And months since origin. We're going to do a cheat right here. We're going to load Q2. Watch out doing this. That just helps us spell it correctly and not worry. We could also use the structure. We're going to predict that as long as it lets us. And now let's go ahead and pull up. Let's just do another quantitative here. Another quantitative, more hit rate. Sure. I might not use these because if I don't know what the variable means, it makes it a lot less fun. Maybe we'll go back to doing the good old survey data. It's just easier to interpret. Let's just see what comes out of this. See what comes out of this. Whoa, oh my gosh. Yeah, I think this is a pretty good graphic right here to analyze. And we should see, and if we look at this, oh, you see, these are tough test questions if I ask you this. What does this far right region indicate to you about, I think this is a very fair test question because it goes to, do you know how to read this plot and what it's telling you? What does the far right region of the plot with the larger circles indicate to you about the X? So that's how I would specifically ask the question. Let me not go too far away from the microphone or they won't hear me online. But what does the far right region indicate to you about the X? Silence. What is leverage? When you get on a seesaw, if you jump down in the middle of it, do you have leverage? The answer is no. So having leverage means you're extreme in your what? Your X's. Where is the center of the seesaw on this graphic? If you remember we did this in class, I had people tell me where the center of the seesaw is. 0. Because something at the center of the seesaw has 0 leverage. This is an absolute distance of leverage. The more leverage you have, the further you are away. Because there's no such thing as negative leverage. You just have more leverage when you're out here and more leverage when you're further over here. Does that make sense? It's an absolute value of how far you are away. It's calculated a little bit more differently, but it can be thought of that way. The further you are away from the center, the fulcrum, the more leverage you have. So what we are seeing right here with these 5 points are 5 extreme outliers, and they would be in the X. So let's find this by just looking at a histogram and confirm what we already know. So let's do a histogram of Q2, $, and this is the X, and we should see extreme values right there. Those are the extreme values that we saw that are so far away. If you compare this to the previous graphic, do you see this kind of flow where there's a peak right here? Do you see that? And then there's a small tail, and then there's those few points. The amount of dots registers the amount of points, as in when all the things near the center here, there's a lot of dots in here. That might even be a whole ton. Yeah, those are little tiny dots that you can barely see right there. Just tons of things that have no leverage and no real residual. So that is the X space on this plot. Let's do a little more traditional one here by loading up our data survey 10, lowercase. Survey 10, does that have the nice neat names? Probably. STR survey 10, let's take a look at the data. And I will post this afterwards, this file, I should be able to save it, send it to myself. You can kind of see some of the things we've talked about. So if you want, just take notes on what we're talking about. You don't have to run all the codes. Like you can, just write right here a little thing and put hashtag talking about influence plots. When we change topics, remind me, I'll put a topic header right here. And let's put right here, talking about take home. So we got little headers in there to keep us straight on what we're talking about at this point, and you can go back and look at this later. Do not focus on writing every code I write. You will get this. Does that make sense? Focus more on the understanding of what these graphics mean, because remember, the take home is code. The in class is communication. So we're loading up, we're looking at the structure here, nothing too crazy, just getting an idea for the variables. Let's reload in LM, model 2, linear model, and we're just getting a basic idea, height and weight, classic stuff. Using weight as our X predictor, not that kind of weight, DARTA. Here we go, and let's get that influence plot. Here we are. Now we see that there are some people that are extremely far away from the center of the axis. Once again, this is not the center of the axis. This indicates to us a point that has high leverage. I might not ask as many questions tonight. You guys are like super focused. You're like, teach, Brian, teach. So this is where we have high leverage. Once again, 68, 95. 5% of the points by random chance would fall outside of -2 and +2. So these are the unusual occurrences. They could be due to random chance, but they're unlikely due to random chance. This literally goes to the 0.05 rejection rate. So things outside of 2, -2 and +2, occur 5% of the time due to random chance and thus are unlikely. So we have something here that has an unlikely large residual if they're outside of this bound, the Y space. And then we have something with extreme leverage. Leverage plus deleted residual equals influence. Leverage and deleted residual, which you see on this screen right here, leverage and deleted residual equals influence. There are equations to solve for the influence, and that's what you're seeing with the size of these circles. The size of the circle is the size of the influence. Now, there's other influence plots that do it with kind of a bend to it, because obviously there's some circles that are bigger over here that are not as big as this one or about the same size, because the more leverage you have, the more influence you have, right? So this is just one type of influence plot we use with very basic rules. Cutoff for high leverage, cutoff for high deleted residual. And if we're outside, as in this region right here, or this region right here, we would say the point has undue influence, too much influence, i.e. the circles are really big. As you see, there's a big circle, that one's not as big. Just with these types of rules, we did not flag that point. The flagged points are then put over here into the output, as you see right here. I can actually see it on my own screen. The flagged points, that's actually a good idea. The flagged points are put into the output there to tell you the numbers of them, and you could simply go to the data frame and look at them by going right here and doing Q2. We'll get a lot. Oh, this is not Q2, yay. What am I doing Q2 for? Survey 10. I wonder if I do this. $ weight. And let's look at just the weights of these individuals. And I believe we'll get that. 251. Got to concatenate this. Concatenate 251, 409. And if we do this as a vector, we should see they're going to be pretty extreme. 75, 270, 250, and 260, but the model's over and under predicting. It's more over predicting a lot of them. So you see we get them in this order. They might not be directly in this order, but these are extreme weights, as you can tell. So these are extreme weights. Kind of hard to tell which is which, because remember, the points here are the actual average weight. That's the pure center average weight. One last thing, I just want to make sure I give you all the info on this and then ask if there's any question about influence plots, is the Y space. Let's look at it, and we'll kind of identify a point right here. The Y space is how far it is away, and we can kind of identify. This looks to be our 260 individual. Yeah, there's the 260, there's the 270. Do you see that? 260, 270, and this point right here, I think, is that point. They're pretty far away from the model because the model would have a deleted residual of 0. That's where the line goes through. And so this point right here is pretty far away from the center and pretty far away from the model. So we look at something that's pretty far away from the center and pretty far away from the model. Here is our person who was 75 pounds, who's also 6'3". They are my height and 120 pounds less than me. That's, I don't know about that. That's, I mean, 75 pounds and my height. So that person was in here. They are point number 544 in the data frame. So actually, if we go to the data frame, the last thing we'll look at right here, if we go to row 544, all the way down here to 544, we will see here we have a male who is 75 inches tall. And what do you think this guy actually did? Do you think he's 75 inches tall and 75 pounds? Just double entered his data, right? At that point, I'd be willing to throw that out. We talk about not throwing out outliers. But when you look at him in the data set, look at that. I mean, he's so far off the model, and no one else is even down here in these weights. At that point, I would say that is just a point that was misentered data. I would toss it. It might just be that one thing. If I saw other suspect things in his data, I might toss the whole row. But these are decisions you have to make after investigating the data. We don't remove outliers. We remove bad data. That's a cool thing right there. So that's the whole influence plot. Do you guys have a favorite topic you want to hear more about right now? You're like, oh, Brian, man, indicator variables are so cool. What do you guys think? Big topic of the day. What is the next topic? Brian, please explain to us. Well, good review. Partition models. Oh, my, partition models. Let's build that tree with that CP. So let's build a partition model. So let's pull up some build tree right here. So to build the tree, we just need to feed it y tilde x. So let's go in here and build a tree to explain somebody's weight. So y tilde dot, and then let's do comma, data equals, survey says 10. So now we run the build tree here. Here we go. This model looks pretty good. Actually, we got some rather interesting results. The results right here on this model show that we have we got a 9, it says right there, 9-foot tree. But our best tree is also our 1 standard deviation rule. The line going down right here is also taking up the dotted line. Those are on top of each other. So what we could do, since we're not using a random seed, and this is kind of a good thing to know, since it's doing a random seed right here, we will get different results. So I just reran it just to get results to show you both lines. Where we have the dotted line is the lowest one. And now we have that the best tree is a 7-split tree. The best tree is a 7-split tree. Now, many of you probably had your assignment graded this morning. Assignment 12 was a 12, activity 13, numbers. Assignment 12 was graded a little bit easier, so make sure to look at the key to make sure, be like, did I get everything right? Because there's so many ways to go wrong on assignment 12. But we really looked for if you use the training and the holdout. So some people may have gotten hit on their grade because they use EX9 birth weight or the NFL data set instead of the train data set. And make sure on your take home, if it says make a predictive model with a training and a holdout, do that. I think there's one that says you'll use 2 seeds twice, right? You guys on that one yet? So you'll be using, when you make your model, the train to see how it does on the holdout. Which when you get to Seaver's class, next time he does this with his students, he'll be like, wow, they all did it correctly, but they did this wrong. So, I love Dr. Seaver. Oh, man. I was disappointed. I was like, but I teach them this. I show them. So here we are. Our best model is the 11-split tree. You see that right there, which I'm hovering over right now. The model we want to use, because 1 standard deviation dictates we can have this much as a crossover validation error. So we just barely make it here, and we barely don't make it here. So let's go ahead and make that tree with rpart. We'll give it a call of a tree. Doesn't matter what we call it. We're going to call the rpart command the rpart command. Rpart. And all we need to do is take our code, drop in, and we need to add the extra CP argument and go up here to our 7-split tree and do Brian's favorite rule of look at the numbers in notation. And so that has 1, 0. Are the CPs of those trees virtually identical? Thank you, output. 1, 4, 7, 6. Cool. We should have a 7-split tree now. Let's visualize the model. I believe it's visualize model for this one. All those different commands. And we should have a 7-split tree. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8. Why is there 8? Because if you take a ball of clay, how much data do you have? You just have a ball of clay. You have how many things of data? 1. So every time I split it, if I split it once, I now have 2. So if I have 7 splits, I have 8 n pieces. Does that make sense? It's confusing because you're like, wait, 7 splits, why are there 8? Splitting something 7 times makes 1 additional component because you're taking something and splitting it. 1 split equals 2 things at the end. Hopefully we don't have some chicken scratch right here. Oh no. Is there a way to zoom in? Where's my ggplot? Oh, am I not? Ah, that's good enough, right? It's a little, I'll read it to you if you want. Okay, we want to predict Brian's weight. How much do I want to weigh? Are we predicting weight, right? I want to weigh, what do I got to answer? I want to weigh, I get down to like 165 and feel like, Brian, you look horrible. I'm like, I weighed that in high school. They're like, you're not in high school anymore. So, that's what they tell me. So I want to weigh 180. That's a good weight. 180. And what else do we need to know? Oh, this is going to be interesting. So is Brian's desired weight less than 166? The answer is no. Is Brian's desired weight less than 196? Pretty good. I weigh about 195. You could take your own path right here. If I wanted to weigh 200 pounds, you'd then have to ask me what? Oh, look at this. These are the people who think they're athletic, and athletic people generally what? Think about athletes. They generally weigh more. So these are probably like a lot of football players, basketball players who survey and being like, oh, I think I'm very athletic, and I want to weigh more, because that's, all these people are like, I want to put on weight. I'm like, you're crazy. I don't get you. So number of body piercings is probably going to male-female differences we see. It's probably coupled with that, sort of looking variable. It's a lot of desired weight. You just ask someone how much they want to weigh. You can get a feel for how much they actually do weigh. But there is variation, especially with the sport variation here. And then really these are the middle weights. And then you're kind of getting down to the male-female, where this is the no right here. Do you have, and look at this, 1.5 is such an interesting number. Why is 1.5 an interesting number to partition on? Can anyone have 1.5 piercings? No, you get it like halfway through? No. You can't have 1.5 piercings. It's splitting apart people who have 2 or less than 2. Why is 2 piercings an important number? Yeah. Anyone have 2 piercings that are just 2 ear piercings? There we go. See a lot of women, 2 ear piercings. That's it. So, I mean, guys can have 2 piercings, guys can have 1, women have 1, women have none. But 2 is probably a lot of ear piercings, and that's a lot of women. So this right here is splitting right there. It obviously didn't split by the start, but that's probably a lot of gender differences down at the bottom, which is interesting. Who knows? But 1.5 is a pretty, okay, that's a nice place for it to split. Does everyone understand how to make predictions with trees? So we kind of talked about how to make a prediction with a tree. We didn't make this with train data. Am I going to have to do some train data here? You guys want me to do some train data? Let's make some train data. All right, so train rows. We'll just name the train rows. I'll just call it TR. You guys might get confused. Train.rows, that's just the name. Dr. Petrie uses a lot. Now we're going to, so let's say here, let's go to building a predictive model. What we could do, and I'll say this, if I just want this to be my best sort of, doesn't like the ASE of the tree, maybe it'll give me in the summary. I think summary gives ASE of tree. ASE in this output. Where's my ASE? Jeez. Let me save the tree's already saved. Let me see if I got somewhere in there. Tree. Is there no ASE? Well, I'll be. Formula, yada, 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 yada. We won't worry about that. We really use partition models for predictive modeling. So let's still build a predictive model right here. Predictive model using a tree. We would focus more on the AIC of that. We'll do some AIC output in here in just a little bit. So let's go ahead and make some train rows. Let's go ahead to our survey 10 data frame. Not do that. Let's go ahead and sample. So we are going to sample 1 through, tell me the number we're going to sample through. We're going to sample numbers 1 through 699, because 699 is the number of rows. Do you see it over here? Number of rows in survey 10. That code right there says sample 1 through 699. That's the colon right there. And then we're going to take, let's do an 80% partition of it, and we're going to take 80% of the number of rows inside of survey 10. This is just a number right here. I just want to make this clear. All this is the mathematical formula to find 80% of that, and then it'll round accordingly. All this is, once again, is 1 through 699. So this will make a vector of train rows right there, which is 559, which is the number you see right there. 559 random numbers given to me. So now we are going to go, we're going to call our train data set. We're going to go inside of survey 10. Lots of stuff bouncing around my head. Nope. That autocomplete though, and that is nice. Train rows, and there we go. We got some train, we got some holdout. You know, you don't even need to copy paste because it just does it for you. Whoa, not the train rows. So we take train rows and then we take not train rows. One thing I see that, and I think maybe OneNote has a problem. Remember, this is 2-space. So when you're building something in 2-space, you need rows, comma, columns. So if you don't put that comma in, it just destroys everything and you see some bad code happen. So we just built it right there, and now we're just going to run the same thing again. But let's go ahead and run the same results and build our predictive model. We now have a training and holdout, and let's do it on the train data. So now we see the suggested CP is this. I'm going to simply copy paste it. And then I'm going to take my output here, drop this in, round it up, copy the line, reverse time, drop down here, paste the line. Got it. Good. So we got our tree built. This is the CP suggested me, rounded just up a little bit. As long as that other CP isn't insanely close again, it's not. Remember, if we meet this CP, as in if we are lower, we will make a split. Does that make sense? If you meet this CP right here, you will make a split. If I put in 0.00741, do I meet this CP? Do I meet it? Do I meet the requirement? Am I below it? 0.00741, am I below it? I am? Wait. 0.00741. Am I below it? Because it's 0.007405. I am above it. So since I am above it, we stop right here. Does that make sense with the number I enter? It is above it, I stop. So I have made this tree, once again, this is an 8-split tree. Let's visualize just to check. Never hurts to visualize and make sure you have, I've overstored my tree, and now we should see an 8-split tree. 1, 2, 3, 4, 5, 6, 7, 8, 9. Go ahead. Did I not use the train data? Oh no, 20 points. Brian's copying code and not fixing it. That's called overfitting. Or wait, so I'm using the CP. I might even get the wrong tree. I might have lucked out there. Thank you. Sorry guys, catch my mistakes. We still have a 9 split right here, but if you notice, the tree looks different, right? Is it different? It is different. Thank you. I'm throwing a 100-pointer out there. Sorry, I was copying code and I changed the train before. You caught it, I didn't. Nice catch. So I just try to go too quick and copy code. So you are very correct. We get something a little bit different here. Remember, we are using only 80% of the data now. So with this 80% of the data, we get a different tree. Once again, Brian goes to the right. Then does Brian want to be less than 218 pounds? Yep. Then I go to the left. Does Brian want to be less than 196? I then go to the left again. I end up right there. I think that was my prediction before, right? Hasn't changed much. And now we can see how well the model works with the generalization. Let's see how our model from the tree generalizes to the holdouts? I don't know. Oh, ooh, this is a good example. Yeah, I don't like it. Explain to me how well your model generalizes. Well, here's some good questions for this. Like, just think of the questions Brian could ask. You get this output. What does it mean? Your boss is like, what do those numbers mean? Explain in context, and these are things you should be writing down. Explain in context the RMSE of the train. RMSE, just tell me blah, blah, blah. RMSE is typical miss we make when using our model on the data it was created from. Did everyone hear that? The typical miss we make when using our model on the data we created from is about, on average, 15 pounds. I'm rounding it. You can say the decimals in the test or just write them out. The typical miss our model makes when predicting on the data it was made from. But then we go down to the RMSE holdout. RMSE, start me off again. What is it? The typical miss. The typical miss our model makes on brand new data, the holdout. You can say the holdout, it's brand new data, the model's never seen it, which is our inclination of how it will work on new data. Because is this data any different from any other data it would get? Well, we hope not, because we randomly sampled our data. If our data is a random sample, then a random sample of our data is a random sample. And it's a lot to say, I'll repeat it. We took a random sample, so if we random sample our random sample, that's just a random sample. So this is just as good as any new data. And so that's the typical miss is 22.32 when we use our model in pounds, 22.32 pounds, when we use our model to make predictions on new data that the model has never seen before. Do we like that or do we not? Answer. Why do we not? Throw down that math for me. Throw down that math. That's why when Brian drinks a Red Bull. That's why I only drink coffee before class. You know what we can do? We can cheat. I showed a few people this in my office. Well, let's call this RMSEs. So let's do RMSEs and do the RMSE holdout over the RMSEs train. And what do we not want to see here? More than what? Yes, and technically in this instance, more than what? 1.25. Does that make sense? Because in this instance, I'm not doing minus 100%. But does it make sense that 22 is about 50% bigger than 15? Think what's half of 15? 7.5. Add that on, you get 22.5. And that's what we see here. It's such a nice, neat number. But 15, half of 15 is 7.5. Add that on, you get 22.5. So when you look at your math, make sure it makes sense. Is that about 50% bigger? Yeah, it is. Is that good? The answer is no. Because we do expect our model to work worse on the holdouts, but we don't want to see it work more than 25% worse. I know that seems like an arbitrary number, and it kind of is. It's not like if it's 26%, it's horrible, and 24%, it's good. The closer it works, the better it is. Like the better your model generalizes to new data, and that's a good thing. That's why Dr. Seaver in his class has people using 3 holdouts, because he wants to see it work once, twice, and 3 times. And if it works 3 times in a row, do you think it'll work again? Yeah. Maybe we got lucky on one of these holdouts, but if it works 3 times, your model works on new data, and you're pretty certain of that. Because he might be telling someone to make investments with this data. He might be telling a company to discontinue a product, to hire new people. The company says, should we hire new people? Make a model that explains what our revenue will be after we hire 20 more people. He makes 3 separate holdouts to test to see if it works, and they all say it will work. So he's pretty certain when he goes to them, he says, you should do this or you should not. And remember, we don't try to figure out what we want. We try to figure out reality. Our models should reflect reality. You might say, no, this is a bad idea. He's a consultant, and his job is literally, I'm trying to tell you the truth. I'm trying to tell you what will happen by peering into the future. And so the capstone class has really been going into that. And it hurt when I heard they built their models on the holdout. No. The holdout is the graduation of your model to see if it actually works. And that's why a lot of the points in the latest assignments have been so drastic, because it's a huge conceptual error to build your model on the holdout. We have one more big important concept in this section right here. We've done a lot on predictive modeling right here. AIC is a little bit easier. The other big important concept we've seen, but we really didn't mention what it was. It's right here. The other big important concept that you should be writing down as I speak about it is the crossover validation. What in the world is this? The k-fold cross-validation process. We talked about train, we talked about holdout. But how do we look into what the holdout might do with our what? How do we look into the RMSE holdout and peer into the future of what might be? The validation. The validation is the middle ground between we make our model with the train, then we estimate how it will do on new data. To remember, to go back over, the training also has in it the validation because it moves throughout. If you have k-fold 4, then the first fold has the validation, then the remaining 3 are used for train. Then the validation moves to the next one and you make a model. Then the validation moves to the next one and you make a model, and then it moves to the next one. So the validation is used to make the model in all but one of the instances. So it's not really a holdout, but it kind of is. It's a holdout all one time and all but one time it's in the train. So with this in mind, we're not really making a holdout, but we kind of are. We're estimating, as in when it says over here, the relative crossover error or the estimated generalization error, depending on the model we're building, how we think it will work. And this is how we think it will work. And interestingly enough, this model does not exhibit much what in it. There's not a lot of what as we increase the splits in the tree. This model does not fall prey to major overfitting. So remember, this is an estimate of how it will do, because remember back in Stat 201 where we say if you split the tree more, R squared will go up? That's true, but that doesn't mean it'll work on new data. New data that's brand new to it, it might fall apart on. So how do we know that? We estimate how it will work on new data with the RMSE validation. That is the typical miss we estimate that it will make on new data, the RMSE validation. RMSE train, the typical miss it makes on the data it was created from. RMSE validation, the typical miss we estimate it will make when we use it on a new model. RMSE holdout, the typical miss it makes when making predictions on new data. So good stuff right there. All this heavy stuff. Let's see. We'll keep talking. Let's talk theory on trees. Maybe put a timestamp in here. We've been going for 45 minutes, so let's say, man, I wish I had told you guys to clock it at the start. But I'm gonna look at my watch every time we start one of these, so that way you can go to the video and maybe get a timestamp on it. So, you can obviously look at the video and see where I'm at on the screen, but this will, that's probably easy enough, right? So with this in mind, when we make a decision tree or partition model, same thing. Stat 1 called decision trees, in this class called partition models. They're just a more general global term. What we're doing is we are figuring out, we're going to the very start of the data. Let's look at a tree. Okay, let's look at a tree. The way it starts is it goes to all the data at the start up here, and then it looks inside of every what? Every single X. And it looks at every single X at every single spot it can split. That's a big process. It just goes through and looks. And it decides to make the split on a quantitative when it can do what? The one that allows it to, say it again. Yeah, and SSE is connected to RMSE, so kind of technically probably. RMSE has a penalty term, so maybe. So yeah, SSE technically speaking, maybe RMSE, they're connected. Smaller sums of squared error, smaller typical miss, but we're trying to specifically look at the SSE, the sums of squared errors. And those are those graphics you see in the notes where you see like a downward kind of trench, and we'd go to the one that has the lowest sums of squared error. Or you could flip it up and the one that reduces it the most, which is what we see when we talk about if we're doing a categorical Y. And remember, partition models can handle categorical or quantitative variables in the X or the Y. So how do we decide upon the split if the variable is categorical? Do it. Impurity or purity, whatever you want to say. We want purity, we don't want impurity. So the graphic in the notes shows the decrease in impurity, which is more purity. What is the maximum purity a leaf could have? Or impurity, excuse me. What's the maximum impurity? Half. Right there, half. And the lowest impurity you could have is 0. What does it mean when it has no impurity? If we were trying to classify males and females, the leaf would all be what? It would all be males or all females. If it has maximum impurity, it would be 50-50. And that's the worst. It's like, I don't know, flip a coin. You'd have, I don't even know if it would, what would the model say? I've never really seen that because I think it would split it. But because it's trying to split away from impurity, so why would it create a really impure leaf? Does that make sense? So yeah, I've never seen the model have a 50-50 leaf because what would you predict? First alphabetical? I mean, it would be just arbitrary then. So that gets into how we make the predictions at the bottom of this tree here. The prediction at the bottom of this tree is going to be based on the what of each group and why. These are theory questions. The prediction at the bottom of each leaf is the what of each group and why. It's, do what? For the other one. It's, do what? The prediction at the bottom of the tree is the naive model, right? That's an easy part right there. But we are predicting a what, why here. We are predicting a, this is weight. We are predicting a quantitative, so the naive model for each leaf will predict the what of that group. The average. Does that make sense? It's predicting the average. This is the average weight of those 94 people over there. The 94 people in that group had an average weight of 116. So if you fall into that group, you're probably like them. So you're probably close to the average. Remember, we have those different lines when we started talking about prediction models, and we talked about breaking the data into parts and then using a naive for each one. But if we flip this, which you did, we were predicting a categorical. Then the naive for a categorical, which is a good break into logistic here, if we want to switch over to that next. If we predict the naive for a logistic, the naive model for a logistic will be the majority level. So it's like, oh, most people in this group are female. Someone else in this group, if they fall into it, would be female. It doesn't mean they are, it just means it's more likely. So if you see down there percentages, I know we were looking at in the office today, Duke, there was an 80-20 for, I think, junk or safe in one of the practice tests. So when you see 80% junk and 20% safe, if 80% is junk and something falls into that, it's probably what? Probably junk. So that's what we try to do here is we say, oh, most things in this group are this. This is probably this also. That's the way we use our predictions in a partition model based on either the majority level for a categorical or the quantitative average mean or the mean for a quantitative. Last but not least, and we haven't mentioned this nearly enough, we do have random forests. And we should understand theoretically what's going on with a random forest. In a random forest, what we do is we create a random subset of two things. Big important things, I've tested theory on this before. We create a random subset of what? Well, the trees, yeah. Well, the trees will be made. We take a random subset of our, I'll start throwing some hints down here. We take a random subset of our, just think about what you got here. Our rows. We take a random subset of rows for each tree. Each tree gets unique observations. The observations can repeat because they're sampled with replacement. So you could get a subset of just 48. It could be 48 300 times. Is that likely? Probably not. So we get random trees. But then each tree, just think about the other thing you have here. Each tree gets a random subset of blankses. Say loud. Predictors, X's, right? So look at this right here. We take random X's and random rows, and we create a lot of trees. We leave some trees to validate. Usually we leave about a third. There's different algorithms, but they all work the same, which means they take random rows and random X's. I'm not that big on the 1/3 of the quantitatives and 1 over the square root of K for the categoricals. Those are just pure memorizations. Different algorithms do different things. But every algorithm I've ever heard of and written to make forests will take random rows. So each data set is different. Does that make sense? If you take random rows, each data set's going to be different. And then random X's, so the way in which the tree decides to split is different. Because maybe, desired weight is a really good variable. Is asking someone their desired weight a pretty good way to figure out how much they weigh? I mean, not always, but you can say, how much do you want to weigh? And I say 180, and they're like, oh, you probably weigh, I don't know, 190, 180, somewhere around there, right? Also, the older you get, sometimes there's a disparity, or males and females. We know there's variables. But will every tree have desired weight in it? Will it? No, because it's taking a random subset of the predictors. So there will be trees without desired weight, which will mean the tree will have to split on another variable, which means the trees will be unique and find relationships that we might not know exist. So with this in mind, they have unique observations, unique people that could repeat, and unique predictors to the tree. So these trees find unique things. And this is great because with more trees comes more understanding. And usually you converge, like I said, I've burned up some computers doing 100,000, I think I did 10 million trees one time, just let it run overnight. Came back, my computer was just hot as kettle pot. But didn't blow up. But yeah, it's bad when you hear your fan go, and you decide to go to sleep. That's a bad idea. They're like, it'll turn off. No, it won't. It's probably why I had a hard drive brick. Enough about me, more about you. So with this in mind, the theory behind it being random rows, random X's, and then what does it do? It grows all those trees huge. And then it figures out what it would predict for each of those and then uses all those predictions to compile into one grand prediction. It's a very weighted prediction using all that information, and it's a very powerful process that a lot of people use. Believe me, the whole idea of random forests is just the beginning of very large, strong model building. That's a big leap, and we just kind of barely talk about it. But you should know the theory on how a forest is built, how the trees are created, that they're grown to the maximum, they have random rows, they have random predictors, and they're a lot better than a tree usually. Because what's better than a tree? Forest. So yes. So that really covers partition models pretty well. I think I said we're going to switch gears over to logistic, right? You guys want to hear about predicting a categorical Y now? Sure, let's do it. Okay, let's see here. What are we going to predict inside of here? 50 points. Remember to send me those points from tonight. What are we going to predict inside of here? I don't know. What are we going to predict? Tell me 50 points. What are we going to predict? We're doing logistic. There's one of two. Give me the other one. As far as I can see. What else could we predict? We'll do gender, I guess. What's the only other thing we could... Yeah, significant. Why? Because at least in our class, we only handled logistic with a 2-level categorical where we have the level of interest is last. Review notes right here. So let's put a timestamp in here. And so we're 53 minutes in. Logistic models. So I'm actually going to run some more code here. So with this in mind, sure, do that to me. So with this in mind right here, let's go ahead and start predicting gender. Gender is such an easy one to predict. Gender, we're going to make model, logistic model. Now, the GLM is the generalized linear model. With the generalized linear model, we have, trying to think gender, brain's breaking. I'm trying to think what I want to predict it. We're going to put in family equals binomial. Number of body piercings? Nah. You guys want to go for an easy one or a hard one? I like percent dateable because I think that's actually going to work. Women do not think people are as dateable as men. Men are like, you want to date? Sure. Women are like, tell me about yourself. So it's like, sad because it's true. So survey 10 says, uh-oh, you guys knew it. Yep, and when you type binomial, it'll try to help you out. It'll be like, let me help. Nope, don't do that. So it tries to add in, because it thinks you're doing like a binomial like equation. It thinks you're trying to solve for the amount and blah, 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 using the binomial. It doesn't realize that that's a command, a function in there, an argument. Okay, so we got our logistic model. You know, let's visualize this and talk about it a little bit. The problem is visualizing it is going to cheat us because we are predicting. Are we predicting if somebody is male or female? What are we predicting here? We are predicting if somebody is in logistic. The level of interest is last. When it comes to reference levels, I come first. Does that make sense? Logistic last, I come first. So since this is logistic, we will be predicting. Say it. Logistic is last, female, male. We will be predicting male. Does that make sense? So when we look at this, we should see, because we could cheat, and we see probability male. That means we're predicting the probability of male on the y-axis. But we should know that before we run it, because we should know it's predicting the level of interest, which is last. Be careful, references and indicators get confusing, and this even permeates through to the take-home to be able to read your output and know what the reference levels are or the levels of interest. So as somebody finds people more dateable, they are more likely to be male. Do you see that? Which means the coefficient, I automatically know that the coefficient for percent dateable is going to be positive. Perfect, right there. We see the coefficient for percent dateable is positive. Well, let's do a tough one here. Interpret for me. Who wants to do it? Be careful. Who can interpret the coefficient of percent dateable? Want to give it a shot? This is a tough one. It's a good one to get you guys on the test on. 2 individuals. Technically, you don't have to say that because it's only a simple logistic. But that's fine. I would not. That'd be nitpicky to me on a test. It's only simple logistics. So 2 individuals. Where? Go ahead. 2. No, I scared you. I'm done. 20 points still. Give it a shot. Anyone else want to give it a shot? You'll remember it if you do it. You'll be like, oh, during the review, yeah, that's what it was. There'll be interpretation on this test. Otherwise identical is what we use for their multiple when there's other things, because we're changing this by 1, right? So 2 individuals, 50 points wants to do it. This is their last chance to correct credit. I won't be doing it during the test. Go ahead, Maddie. Percent they find people dateable. That's what that was. Percent. It's a percent, yeah. By 1%. The person who finds people more dateable. Bingo. Did you interpret that right there for me? It's confusing because that looks like 1%. It's not 1%. When we say 1 here, we're talking about a unit difference of 1. Does that make sense? 2 people who, got me doing it. 2 people, no multiple. 2 people who differ in their percent, they find people dateable by 1%, not that number. The person who finds people more dateable is what? More likely to be male. You say, but Brian, that looks like a constant change. The answer is no. I don't think I can change. We're going to change the percent dateable here to just weight or height. Do what? 2 people who differ in their percent, they find people dateable by 1%. The person who finds people more dateable is more likely to be male. They're more likely to be the level of interest, because this increases the probability of the level of interest. Does that make sense? So let's go ahead and run this with height to show you that in the logistic curve, it is not a constant change. 2 people who differ in their height by 1 inch. Just tell me, the person who is taller is more likely to be male. You know that. You know that about the world. But wait, how much more likely is this person than this person to be male? They're both like all going to be female. If you're about 5 feet tall, you're probably female. It doesn't mean you are. It just means you're very likely to be female. So with this in mind, all of a sudden we see the change in the sigmoidal curve right there, because the sigmoidal curve is not a constant change. That is why we do not interpret this coefficient. We do not interpret this coefficient. Another great question, at what point do we start predicting that somebody is male? At what point would we start predicting, using my model I've created, that somebody is male? I'm trying to solve it in my head and beat me to the answer for 50 points. At what point would we start predicting that somebody is male? And I think I have it. What do you say? Yes, basically. It's almost intercept over slope. It's technically, well, it's not intercept over slope. It would be negative B0 over 1. What's 7 times 7? I mean, what am I doing? B1. So what is 7 times 7? 49. What's 7 times 70? You notice this is going to go into it, I believe, about 70 times if my brain is not broken today. So let's do this right here, negative B0, which makes it a positive. Does that make sense what I'm doing? All decimal place accuracy for which we can see. Negative B0 over B1 is the 50-50 breakpoint. And we should get about 5'9" by my estimates, which would be 69 inches, almost 69, 68 inches, some decimal change. You have a friend who's 5'10". Do you think they're male or female? They're probably what? Just take a guess. Male. You have a friend who's 5'5". What do you think they maybe are? Female. Doesn't mean all people. It just means in general, more likely. Like at that point, you'd start predicting. Technically, at the 5'8", if someone was 5'8", you would predict because that's 60 inches, 68 inches. 5'8", you'd predict female. 5'9", you'd predict male. If your friend's funky and says they're 5'8.5", you'd predict what? If your friend says I am 5 feet 8.5 inches, you'd predict they are male. Because after this height, we're over here, and they're more likely to be male. That's the exact breakpoint. Go ahead. The coefficient. Sure, I'll interpret this coefficient here too. Remember, in logistic, we do not interpret the value of the coefficient. So we can interpret the coefficient even if it's a multiple. I'm going to do an interpretation of a multiple logistic now, just so you can hear it. Let's throw into here, what other variables should we throw in? Oh, let's do interaction, right? What do you say? What do you say? I thought you were giving something. What is it, percent more attractive? Own attractiveness, where's that at? Own attractiveness, I love that. Let's own attractiveness. Conceited people. Okay, so now we should have 3 things in this model. When you see code like this, you should be able to tell me what's in the model and kind of think through what's going to happen. This is going to carry through model hierarchy. Model hierarchy states that if you have the interaction between height and own attractiveness to carry through, to maintain model hierarchy, preserve, that's what I was looking for, to preserve model hierarchy in your model, if you have an interaction, you have the whats? You'll have the 2 variables. Does that make sense? So we'll have interaction, variable 1, variable 2. Technically, variable 1, variable 2, interaction. This preserves model hierarchy. I think we can visualize this. Oh, you look at that. Let's look at the summary. We got our 3 variables. Let's do some funner interpretation. The coefficient of height actually depends on people's attractiveness. But the good news is this, that we see that in all instances, and we got a bit of a weird graphic over here, that the coefficient of height is always what? The coefficient of height is always going to be, look over there at this, the coefficient of height is going to be what? Positive. And the one with the strongest, the one with the strongest is going to be the one that is sloped the most with the highest coefficient. So I know this is not categorical, we kind of wish it was for this example. When we talk about the strongest way that it is, when you look at own attractiveness, as own attractiveness goes up, plug in 100 here, that times this by 100, it makes this stronger. As in, when we look over here for high levels of own attractiveness, you see all these lines gathered up, and the red line shoots up faster, it's steeper. It's more up, it's steeper, it's stronger. So with this in mind, the stronger something is, the higher the coefficient, and you can look, and when I say higher, I mean in terms of absolute value. Things that are steeper in either direction are stronger. They impact it more. By changing the scale here, it changes it quicker. The ones that are weaker are flatter, which they don't change it much. As you go across that variable, when it's weak, it doesn't change much. So that's big stuff right there. So good job for you people working. Someone's like, go back, watch the video. So with this in mind, let's interpret a coefficient here. Go back to the in-class, not that we ever left it. But interpreting the coefficient of height, it does depend. This is like your weather question. Remember it said, does the coefficient of weather, is there an easy interpretation? Right? Remember that one on the one assignment? Is the coefficient of weather have an easy interpretation? The answer was no, because the impact of weather would depend if it's a working day. It would depend on other things like what's the humidity, the average humidity. Do you think, oh, it's a Saturday and it's raining? Oh, it's a light rain, it's not humid out. It's a Monday and it's raining and it's really humid. You're gonna go rent a bike? No way, no how. You're like, Monday morning, I'm not renting that bike. I'm driving the car to work today. So with this in mind, the coefficient of height is positive in all instances. Plug in the lowest value of bone attractiveness, and this is still positive. You can see that over here. Plug in the highest, and it's even more positive, i.e. stronger, further away from zero. So I could kind of interpret it, and I'd feel all right to do that. The coefficient of height tells us two individuals who are otherwise identical. The individual who is taller, in all instances, is more likely to be male. And the strength of this relationship increases when the person finds himself more attractive. Does that make sense with your world? When someone's like, I'm so attractive and I'm so tall, I'm a dude. Maybe? It's like people who, it's like the more attractive someone thinks they are, and so it's like, I think it's guys and their egos, right? I can say this because I'm a guy. Brian, you're talking bad about guys. I'm sorry, guys. I'm sorry. So sometimes the models make sense with your world. But someone counters me and they say, Brian, that explanation you gave is crap. That's probably not true about guys. It's probably due to, see it in the output. They counter me. They say, Brian, I took your class. You're not reading all the output. That relationship you explained about guys thinking when they're so attractive and they're so tall that strengthens the relationship of height, that relationship is probably, say it louder, not significant due to random chance. You'll notice here that the sigmoidal curves don't change that much. The stronger the interaction, the stronger the change in the strengths. You could have something that's just as strong this way as it is this way. It's just different, sign. So this here is not a strong interaction, as denoted by the lines don't change that much. In the sigmoidals will change. If they change enough, they'll go through each other, and they do technically do that. Blues on top, blues on bottom. So they do go through each other, but it's really not that strong. Let's find a stronger interaction. Gender, height, maybe with weight. You got to pick things that are lame. It's stronger. Yeah, if you look at how much more those bend, which one here is blue the strongest? You can figure it out mathematically. Oh, did I not do it? There we go. This is a significant interaction now. Everything in this model is significant. I think blue is the steepest, right? So weight's small. Yes, because weight decreases the coefficient of height. Do you see that? As weight goes up, the coefficient of height decreases. So when weight is small, we have the strongest, height has the strongest influence, i.e. it changes the probability the most. So it's the steepest there. So all that good stuff. Because of the scaling, you usually don't get great graphics. Usually one of them turns out great unless you use set the scale with the X limbs. So some good talk about some interactions. And you guys want to interact on let's do let me change it. Yeah, that's what I'm going to do. I'm going to interact on a categorical. So let me do that. Interactions for a linear model. About one. Okay. What are we going to do today? So let's predict. I know we're doing a lot of height and weight stuff. It's just easier to understand. Let's do linear model, not LM. M3. And linear model. Let's predict somebody's height, and we'll do it from their weight and gender. Nice and easy stuff to talk about. How many variables will be in this model? How many coefficients? How many variables? How many? many? 3. Because it carries through model hierarchy, so we do have a multiple regression right here. Let's visualize this model. I think I'll visualize with this. There it is. This is an indicator regression, and it looks like we don't have, I included the interaction. There's not really a slope change, so since the slopes don't look really different, I'm guessing the coefficient for the interaction is really not there and not significant. Yeah, and does everyone see how I saw the slopes are not different? So when I saw the slopes were not different, I knew that the interaction was not significant. The more significant the interaction, the more different the slopes are. So this is not a significant interaction. Let's do significant other just to see if we can get something here. That's missing an N. That's significant other. That run? Cool. Oh, look at that. Look at that. We got some crisscross. We got some crisscross, which means not significant. It's not, but you notice the p-values are lower. And this is a good thing right here as we see this first one we had a p-value of 0.85. The differences in the slopes we are observing is the differences in the strengths. For this previous model, the strongest one right here would be which line is stronger, has a stronger relationship, males or females. Which one has stronger, male or female? Which one? It's hard to tell via the visual. That's a good test question. Which one's stronger, male or female? Male. Because you plug in 1 right here for male, and then the coefficient of weight will increase by that. Does that make sense? The coefficient of weight for males, you plug in a 1 right here for males in the output. So you would solve this equation with a 1 there and a 1 there, which means the intercept for males, look at this. Do you see the difference right here? This difference between this and this line, the intercepts, if it was the intercept, we'll pretend. If this was the intercept, the difference between these lines would be how much exactly? How much? 4.811. That's the difference in the intercepts. That term right there is the difference in the intercepts. It just adds to the intercept. The intercept for females is 60.49. The intercept for males is 4.811 above that. The slope for males is 0.0013 greater than 0.032, which means it has a greater slope. It's hard to see, but the red line is a little more sloped than the black line because males have a slope that's much greater. But it's easier to see in our next output. And although these aren't significant, we can still look at them and talk about them. It's easier to see in this output that which has the greater slope. Yes or no? Just look at that and you can see yes goes through it. The red line goes through right where my hand's at. It goes through, so it has to surpass it. It has to have a greater slope. So when you look at the coefficient right here, for the interaction, weight, the coefficient of weight, if we put a 1 right here, we will increase the coefficient of weight by that much, making it stronger. So with this in mind, significant other actually decreases the intercept. You see if we continue this, the intercept will be lower. So the intercept is decreased from the reference level of no, because it's first alphabetically, and we would have a lower intercept and a stronger slope via this. This one changes the intercept, i.e. you just put 1 in here, and then like terms go to the intercept, and then you put in 1 in here. Let's write one equation so we can all see this. Writing the equation could very well be on the test. If you want to write your general equation, which we don't usually do, we are predicting. So it doesn't help that I'm blind and I don't like to bend my neck. I can pick my poison. So I am predicting height. So predicted height equals, right there, take that, not that. There we go. Too many clicks. So, and we should technically hashtag this because this is not code. So there we go, predicted height equals, double click, go right here, plus this times weight, and then plus, technically a minus. Will it take the minus? Nope, it didn't. That's fine with me. And then we put in significant other yes. We can put sig yes, just to abbreviate. Start another tab, hashtag, and take this, and plus coefficient, weight, And to be a little more easier on it, we can just do the multiply by sig yes. So if we were to solve for this, when we solve this equation right here, we could actually use it to make predictions. Let's predict Brian's height. Weight equals 195, whatever I'm saying I weigh today. So there's my weight. And let's write our equation right here. We have the equation pretty much written for us. And let's write it. Brian does or does not have a significant other. This is on the test. we were in a lab today, and we saw someone who knew me, and they were a former student. They're like, "Is this the fabled girlfriend?" And I was like, "Yeah." And she just looked at me like, "You." All right, so let's put in a what for significant other? 1, and let's put in a what right here? 1. That actually removes all this right here because these are now on. This right here would be a coefficient, which is just going to go to that. Does that make sense? This should solve, fingers crossed. Attempting to apply non-function O. Thank you, R. One of your first lessons. Remember this? Comes back to bite you. There we go. Nope. Not so bad. We can look at the typical miss on the model. The model usually misses by about 3.5 inches. Brian is 6'3". He predicted him to be about 50.6 inches. I think it's so cool to do this, especially when you have weight right here and you can just plug in. Anyone else with a significant other want me to break their height? You gotta tell me your weight. No one? 50 points. First one to say it. You're like, I had to tell Brian, are you 6 foot, 5'4"? Ah, close. Not horrible, right? Yeah, you're like, did you want to do it too? One more over here. Do you want to do it? Sorry, you don't have to. 25. So actually, and you have a significant other? Good. This model right now, and I'll make that clear. This model right now is only predicting for significant others because if I want to, actually, have I made a mistake here, guys? Because right here, this should change the coefficient of weight. Let me make sure I'm doing this correctly. Because now we should add this to coefficient of weight. Probably going to predict the same. Let me double check my math here because usually I don't write it out like this. Let me change the coefficient of weight, which mathematically I think this is the same. Let me see if the predictions are the same. I'm just simplifying my model. Yeah, that's just algebra, right? That's the same. So when we run this again right here, yeah, that'll change the coefficient. Yeah, it's algebra. You ever get worried that algebra actually works? It's my life. So if you notice, and actually we could simplify one step further because now, and let's do this, this is really good practice right here. I'm going to take my intercept and decrease my intercept by this amount. And here is my equation. So let's write predicted height equals that minus, plus, and let's take this, times weight. Sure, it's gonna get mad if I don't do that if I ever use it again. If you notice, we'll go back through the output just to look at it briefly. This is predicted height when someone has a significant other. Is this equation right here, but could someone tell me the equation, predicted height, for sig no equals what? You see what I'm going to write? Does that make sense? Because if significant other is not yes, it's no, what happens is it turns to 0, it's off. This is also a 0. What's 0 times something? 0, what's 0 times something? It's gone. Gone, gone. You can only have one indicator on. If there were more levels to these indicators, you'd have 3 different or 4 different indicators. There's only one reference. So you notice right here, this equation I just wrote is simply 57.234, all the decimals, plus that right there. So I could use that to predict someone's height for someone who does not have a significant other, and that is the model right there. That is the implicit line, the equation of that line over there. Both those lines are written by this equation. Does that all make sense? Some good writing the lines equation stuff right here. So that's some good work right there. Does that answer you guys a lot of your questions on indicator variables? A little kind of quick review of indicators. How can we see if a multiple level indicator is significant in a model? Here's a good theory question we haven't said yet today. Like handedness. Handedness, let's see. Let's do some handedness models here. Okay, so we're going to just simply take, so let's talk about, we'll put a little blank right here, not over there. Checking the significance of something in a model. Well, if we had handedness in here, let's predict height by weight plus handedness. So now when we get this model and we visualize it, we should have 3 separate lines here. Woo! That does or does not look significant. Does not. I don't think someone's handedness is going to help us predict it. But, you know, we can't. Oh, it already did it for me. I forgot, yeah. I already know if it's significant or not, but let's do the summary, because summary tells us significance, right? Does summary really tell us the significance of handedness, yes or no? It's telling us how significantly different the indicator level, group, I don't want to say level, that confuses terminology. The indicator group left, people with left hands, are from what? How different their line is from people who are ambidextrous, because that's first. I come first, reference levels come first. So the ambidextrous, we see here the difference and our uncertainty of the difference. This is the difference, kind of the uncertainty in the difference from ambidextrous to left. This is the uncertainty from ambidextrous to right. It's how much our uncertainty is on how much they might differ, which is the standard error right there. When we look at this, we have our estimate of the differences, and they're pretty small. Dividing them by the standard error from how much we think they are different from ambidextrous is very small t-ratio. Small t-ratio, what p-value? High p-value. So we do not have significance here. Interestingly enough, the visualize does come back, of course, with the drop 1 test. So let's run a drop 1 test here. With the drop 1, we're going to insert our model. We're going to say test equals F, because it is quantitative. A real quick note on this: if you're doing the drop 1 for if you're doing the drop 1, it's F for quantitative, and like that, I believe spelled like that. It needs to be perfectly spelled. I wish there was more of a check in there, like you did not put chi-squared exactly like this. Did you mean this? Some really fancy codes have that. Like they'll be like, did you mean this? Click yes, and you'll just be like, yes, I meant that. I'm an idiot. But it kind of, you know, and I love my autocomplete. We run it. What do we get? 0.8542, which is the same thing we get when we run that. Same exact result right here. We see something interesting. Why are there degrees of freedom? We don't go into this much, but you can tell me, why are there 2 degrees of freedom for handedness? Because there's 2 indicator variables. Does that make sense? Why is there 1 for weight? When you include, and this goes to model building a little bit, when you include weight, how many coefficients are you adding? 1. When you include handedness, how many coefficients are you adding? There's 3, so you're including 2. When you do a quantitative variable, it simply adds 1 coefficient to the model. Like weight, height, they all add 1 coefficient because you have blank times weight. So that's the coefficient of weight. When you do indicator variables, you have as many levels minus 1. So there's 3 levels, minus 1, 2 levels. So we see that right here, and we see that weight. Well, yeah, the weight is ridiculously significant. And I can kind of tell you the t. Another quick thing we learned, another note, who knows what's on the test? I hate throwing little things on there, but it's something you should maybe know, is what is 20 squared? 20 squared, 2 times 2 is 4. Add your zeros, you get what? 400. It's not quite 20, so it's not quite 400, but the t squared is the f. So we see that right here, that the t squared is the f. Once again, do not need to know that, but this is the sum of squares reduction. Do we want sums of squared reduction, yes or no? We want to explain that sums of squares are errors. We want to reduce the sums of squared. So does weight reduce the sums of squares? Does it? It does. And with that in mind, weight reduces the sums of squares a lot. So it's very, very significant. And this is a kind of average reduction in sums of squares. We'll look at this. Here's the sums of squares. We are not doing it. Not significant right here. Very small f. Very small f, not significant. Small f's are not significant. The larger the f, the less likely by random chance. Higher f, lower p-value. All this good stuff right here. I'm trying to think what else there was. It's all right to look at something that's not significant. Let's do an interpretation here. Let's interpret the coefficient of handedness left. Anyone for 100 points who can do it. Coefficient of handedness left. Are we predicting a probability, or are we predicting a like a number, an average for the individuals? We were predicting an average. I'm throwing you 100 points for there, just going on a limb. We were predicting height, which is a quantitative model. So when we look at this right here, we're explaining handedness left, right? Two individuals who are otherwise identical. So I have to say that now because it's multiple. Two individuals who are otherwise identical, where one individual is left-handed and the other individual is ambidextrous. Does that make sense? Because we have to compare it to the reference. That's why it's called the reference. I'm going to start again. Two individuals who are otherwise identical, but one individual is left-handed and the other is ambidextrous. The individual who is left-handed is expected to be 0.134 taller. So does that mean, who wants to be taller? Who wants to be taller? Take that pencil out of your right hand, put it in your left. Because if you're right-handed, you're the shortest person there is. Not that much. But wait, regression is not physical law. This is just what we observe. Also, this relationship here probably is just due to random chance. It's not significant. It's just due to random chance. So we're not really seeing anything important here. Once again, not a physical law. It doesn't mean if you're switch writing, you're going to grow. We'd all love that or hate that. You know, just choose your height. You can vary by 0.25 inches. You can vary by 1/4 of an inch. That much you can change in your height. If you switch ambidextrous, you start to do that, you just even out. Notice ambidextrous would be in the middle because the coefficient of ambidextrous is what? Not necessarily in the middle, kind of, but here it is, visually. It's 0. The coefficient of ambidextrous is 0. It doesn't change it. Everything else is in comparison to ambidextrous. Our uncertainty in how different this is from ambidextrous. Hints there. That's when we talk about our uncertainty. The standard error is how much we think these might be different from ambidextrous, because that's what the coefficient is. The estimate is how much we estimate it is different from the reference. I feel like I'm on a high tonight. I think when I'm in a room like this, I feel like I have to project more. One time in Stat 2-1, someone actually said to me, "Can you turn off the microphone?" And I was like, okay. I'll turn off the microphone. What other cool models do we have? We've done some partition. You guys want to do a little talk on time series to wrap up? We'll just kind of, I know those are your guys' latest stuff. I don't plan to hit you guys over the head with we didn't really interpret time series models. So we're just going to talk about time series, then we'll do a cleanup with final questions for maybe the last 15 minutes. We got for 30 more minutes. Time flies, right? That. Who was in my office today? I know Duke was. I was like, man, that was so busy, wasn't it? I've been here since I got here at 8. I was doing work at like 7:30. And I'm just like, I needed that Red Bull. So talking about time series. So go home and watch Philip DeFranco. You don't know, anyone else watch Philip DeFranco? Stuart here tonight? Anyone else watch Philip DeFranco? Yeah, kind of. Do what? Oh man, he's gotten better. Go home and watch some Philip DeFranco. Best news there is. Brian's plugging Philip DeFranco. Okay, let's talk about time series. Enough about me, more about you. So, you know what? Let me say this. The good news, you guys can cheer if you want. One class has, I think, 95% completion. The other has what completion? 100%. Oh, gosh. But I was telling my girlfriend, I was like, man, there's got to be someone who hates the class and hates me. So you guys found that one. You got that one person response. He's like, Brian is horrible. Talks about girlfriend the whole time. Learn nothing. I don't know. So I hope you guys enjoyed the class. So with that in mind, time series. I would say there are, let's hit some big concepts in time series. I can't walk too far away from the mic so people can actually hear the recording on this. What was a big concept in time series for 50 points? Let's talk about it. Autoregressive models. We talked about ARIMA models here. The heck, people have to know that this is not code. Models, ARIMA models. The autoregressive model is the idea of using how much we missed a period ago, or a different amount, P being the period, or just when we put it into the code, how many periods back we're going to look at our miss. So in other words, if we underpredicted today, the model will probably underpredict tomorrow. If it overpredicted today, it'll probably overpredict tomorrow. And there's such great graphics in the slides with this. But one of the hardest things for people to see, and I'm trying to think if I have some good time series data in here. We go over to, go back to here. Let's Control Tab. It worked. So let's go time series model. Ooh, wait, I like that one. I like this. It's Wikipedia. No, I will not donate Wikipedia. You select an amount? It makes you wonder at times if it's listening to you. That actually looks like with a moving average. If you notice all the trends, that's just so cool. Let's put in here negative, well, let's do this, positive autocorrelation. Positive autocorrelation in residuals. Residuals. All right, let's do a pretty good positive autocorrelation. I actually just saw the ACF in there. This almost looks like Dr. Petrie's one. I really want to pull out one of the trick ones that I like using on you guys. Show you all the tricks in here. Yeah, this is positively autocorrelated. As you know, in the slides, we have something that is positively autocorrelated, but we could go to that graphic next. Why is this positively autocorrelated? Why is it positively autocorrelated? When, and specifically, when we under or when we overpredict, because the line's over it, the predictions are over it. When we overpredict, we overpredict. When we underpredict, we underpredict. It's not that as time increases, so does our y variable here, which is just called y today. It's not that. That is a positive correlation with time. Autocorrelation is how the residuals are correlated. So tell me, when there's a positive residual, the one next to it is probably what? When there's a negative residual, i.e. below the line, the ones near it are probably negative. So this is positive autocorrelation. To contrast that with negative autocorrelation, your take-home or your in-class asked, and this is great right here, don't focus too much on the graphic on the left. The graphic on the right is what you would see in your residual plot. So in your residual plot, you will see this up, down, 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 up, down pattern. That is the strongest of negative autocorrelations right here. When we see very strong negative autocorrelation, and look right here, we see positive autocorrelation again. That is a residual plot that actually stays kind of flat. But if you notice, when the residuals are low, the residual around it, the residual before it is low. So a low residual would probably explain the next low residual, the previous residual. And when I say the previous residual, I'm talking about what order autocorrelation? First order, the one right before it. But can you do second order? Can two residuals back explain it? Third order, fourth order, and that's the P you're using in your ARMA models that you're making for 11. That's the P you're using, which is the codes in the slides. But you are using an ARMA model with first order, second order, third order to see if a residual 1, 2, 3 back explains your current residual. So there can be different, and this would be known or be able to be viewed. Let's change it so we can look at an ACF. And we should be able to see an ACF. Well, that's a weird ACF. This is a very clean autocorrelation function. So right here, we see a spike at 0. And why do we see a spike at 0? What does that mean? Why is that nothing? It's above those blue lines. Those blue lines indicate significant autocorrelation. Because what? Yes, a zero lag means the residual now is predicted by the residual now. And what percent of the residual now is explained by the residual now? 100%. It's like today we had a residual of +4. Today's residual is thus +4. Sometimes they don't include this, but you do see it every once in a while. I have to point these things out because if you see that in output, you might be like, oh, look, but that's nothing. It's just today's residual is explained by today's residual 100%, i.e. 100% correlation, R squared, 100%. So we get to one. I saw a cool one right here. Is that the one I liked? No, is that the one I liked? There's a better one. Why am I losing it? I saw a really cool one that I really liked. I thought I had more than one. Okay, yeah, this one's good to talk about, though. Okay. So where do we have significant correlation in the residuals? On the what orders? This is probably a larger data set because it's using smaller correlation. Once again, the what order is significant, and we would tackle this. You should know how to read this output and tell me, Brian, I'm going to investigate this. Or how many things? What are you going to investigate? And what else? First order and what else? Remember what the notes say. We'll only investigate the first order, then we'll maybe do it again. So I probably won't hit you guys with that. That's a little tough question. It was meant to be a little bit of a trick. But if something's not significant after, you don't investigate. Because as I said, if you remember I said in class, if we investigate the first and we control for that, the variation explained by the first order autocorrelation might take care of the later orders. Because you notice this kind of flowy pattern that happens, changing that might do it. And I thought there was one, maybe it was this one I was looking at. You would still just investigate the first here and then see if it comes back. But also, this could lead us to do something here. Really weird lag. I do not like how they made their graphic here. This one, oh my gosh. Wow, that's some data right there. You could investigate all the way down to the 5th order right there. So that's some interesting. I mean, this is just really, but this is the significant autocorrelation lag. Does that make sense? The first order, the second, the third, the fourth, the 5th, all the way to the 5th are significant. This is a time series data set. And they're putting some classic ones up here that you would see that if you're not using time series in this and you build a descriptive model, your descriptions might be overconfident, once again in the notes. If you're building a prediction model, your predictions might not be as good. But this is just one topic, and we've covered it pretty well with using the ARMA model, which we're mainly only using the R of the ARMA. We didn't do a moving average. The other topic we really hit upon was the Durbin-Watson. The Durbin-Watson is a test to see if we have significant, this computer is so weird. The Durbin-Watson is a test to see if we have significant autocorrelation. So let's go right here and type in Durbin-Watson output. So when we look at the Durbin-Watson output, lots of different output. We'll go to one that looks kind of like ours. Yeah, might have to run one. Do not like that. Might pull up the notes actually. Let's look at the notes briefly. Everyone makes their output differently. Let's hop over to the notes and just see the Durbin-Watson output because this could very well appear on your test. These computers are actually running off of a mini computer. One of our people here, it's a pretty interesting mini computer. One of our tech people was talking about how these might be the new computers we use, and I'm liking it. It's different. You got to get used to it and its shortcomings, its goods and its bads. We should see the Durbin-Watson here in a second. The time series model is what solved with our model. The time series model is what kind of solved with our model. I'm going to download it. Easier. It is a simultaneous solve. Does that make sense? You guys remember me saying that in class? The time series is a simultaneous solve with our model. So we're solving two models at the same time and using them to make predictions. Let's go here to, where's Durbin-Watson? Model selection, model check-in. Everything has to run slowly, doesn't it? Model checking, it's got to be right here. There it is, Durbin-Watson, model checking. This is kind of our check regression. It's to see if there is any leftover variation in the residuals that would be explained by the residuals. In this instance, we see that there is what? We should investigate the what? The first order. The first order has some, and if you look at this p-value, going back to stat 201, you would what the null here? Reject, and you would say you have evidence for the alternative that the correlation, Rho's correlation on the lag for the first order is not equal to 0. I have evidence that the correlation for the first order lag is not equal 0. Does that make sense? Reject the null, evidence for the alternative. Going one step further, we do see our classic output again, and if you notice, the spike here at 1 is significant. The spike at 4 is significant, but we will focus in on 1. And if you notice right here, the spike on 4 also has a significant p-value. So that p-value there is directly related to that it goes beyond. Also, the correlation was negative and at a greater magnitude than the other one. That's when you look over here, you see that this dips deeper than this and outside of the significant range. And there's kind of a cutoff on what is significant correlation. So the Durbin-Watson is just for us to investigate if there is significant autocorrelation in the residuals. We have one other technique for 50 points. I want to see that hand go up. I want to hear you say it. The other technique we talked about to make a model would be to do what? To do what with our variables? Where's that hand? Make a lagged variable. The other one we talked about in depth a little bit was making a lagged variable. And we looked at the data set, and that made a lot more sense that we're lagging the Y. What might explain what we'll sell this Christmas? This Christmas season, the winter season, our sales this year might be explained by our sales last year. But wait, isn't that what we're trying to predict? We're trying to predict sales? We're predicting sales by using sales, which is the Y. But we're lagging it back 4 periods, which is a season. So the sales this season is explained by the sales last season. That's not autoregressive, though, because we're not using the residual. We're not using how much did we miss by last year. Like, did we overpredict last year? Well, then we might overpredict this year, and that would be a residual lagged 4 times. Does that make sense? The residual 4 periods ago might explain the residual this period ago. It's really hard in classes I've seen where they're like, which of these graphics shows a 4th order residual relationship? And you have to learn how to look for it, and it's not fun. But the negative autocorrelation, just to say that again, which I catch people on the test on this all the time, is the other one is the opposite sign. The positive means that they follow each other. They could follow each other up or down though, right? Does that make sense? We talked about that a lot, and those are such, like, were you there questions. One of the reasons we go into time series is this might be the only time you hear of it. You might go to a company that might say, oh, have you done time series? You might say, oh, a little bit, and we want you to be able to say that. We want you to be able to say, I know what time series is. It's when there's a time-ordered data to the series, like to the data we collected. It was collected period to period to period. And then if we don't consider this, we will make a bad descriptive model that overestimates the coefficients and how good they are. Not overestimates the value, the estimate, but we're overconfident in how good they are, which means we've underestimated the standard error, which is our uncertainty. If we use it to make a predictive model, we will make predictions that are not as good because we're leaving out valuable information because the residuals explain. The lagged variable explains. By saying it explains, it means we can increase our what for these models? Our R squared. It could be better on the holdout. Our MSE holdout would be better. And also, our descriptive models would be closer to the truth. Another concept, which I'm going to end with tonight before questions. If our model is closer to the truth, I'm telling you that it has what? Our model is closer to the truth. It has a lower AIC. And it's way closer to the truth. The difference in AIC is more than, that'd be enough to make a decision. 10, I do agree. 2 is where we're saying they're different. 10 is a kind of big difference. The AIC does not have an interpretation. So AICs have no interpretation. They're just how close the model is to the truth. The lowest possible AIC is, how low can you go? Think of lowest possible. Negative infinity. Negative infinity, 20 points, or I said that, I didn't even see. 20 points. Negative infinity is the lowest possible. It's not 0. That's kind of I could trick you on that. Lowest possible AIC is not 0, it's negative infinity. Because the only way to reach a negative infinity is to have a sums of squared error of 0. And at that point, we'd estimate that our model is as close to the truth as it could possibly be because R squared would be Make me smile. Sum of squared error is 0. R squared's 100%, all 1. Because if you have no error, have you explained everything? And if you've explained everything, how close do you think you're to the truth? As close as you could possibly be. So that's when you get a negative infinity AIC. It's important we know how these work. We mentioned 2 things. I'm kind of just rapid hitting topics now. 2 things have a, have a penalty term in them. The RMSE has a penalty term, which is our typical miss, which will penalize us for adding more variables into the model. R squared adjusted, we haven't even mentioned that tonight. R squared adjusted has a penalty term in it. So it's adjusted for how many variables. That's literally what it means. The R squared adjusted for how many variables. So R squared adjusted can go down. R squared will always go up. You add more variables, you explain more, but you penalize yourself with R squared adjusted. The last one with a penalty term, I know I said 2, but I thought a third. The last one with a penalty term is AIC. And AICC, which is basically AIC for smaller models, where the ratio of predictors and variables or observations and variables is very small, less than 40 ratio. AICC has in it a stronger penalty term. And that's when you use it when you have a model with very few amounts of observations. But AICC is a stronger penalty term. So it really weights against models with a lot of variables when you have fewer observations. So sometimes people use both AIC and AICC to make their decisions. Sometimes people use BIC, FIC, ICOMP. There's a lot more to this world, but Akaike made AIC. Akaike's information criteria, and that's kind of what we use today because other people just trying to tweak it. They take like a Ferrari and they're like, I put rims on it. I put a better air conditioner. You're like, well, you still bought the Ferrari from the Ferrari dealership. I mean, it looks cooler with that stuff, but it's still that they're the ones who built it. You're just tweaking it a little bit. So all models are wrong. Some are useful. I don't know. We put down the midterm, right? He was like, please put it on this test. We know that. We know that. You'll just be in your next test. All models are wrong. Some are useful. George Box. But I literally had someone right next to that on the test. Are you seriously asking this? And didn't fill it out because they didn't know it. And I was like, I'm sorry. Let me just say why we say that. Because even if we made the true model, would we know it? Even if we made the truth, would we know it? So we wouldn't know it. We'd be like, oh, this looks like a good model. It explains 96% of the variation. But whoa, we found the truth. And we'd never know that. So since we'd never know it, we can't even say that we have the truth because we wouldn't even know it. So to us, all models are wrong. Some are useful. If you go into the physics world, you might actually make some true models, you know, actual real physical laws. But our models aren't physical laws. They just describe the variation we see between 2 observations in the population or in our sample that we expect to see in the population. We kind of extrapolate it to the population. Okay, well, I mean, you obviously can head out at any time, but we'll now go to the question answer section of this presentation. What do you guys want to hear about? What are those questions so I can give answers? I'm looking down, that doesn't help. Go ahead, question. Yes, misclassification rate. I have a logistic, right? What do I call my logistic? LM. So let's pull up the misclassification rate of that logistic model. I need confusion matrix, not misclassification. Confusion matrix, LM. Boom, misclassification rate. There you are. You good? Kidding. All right, so the misclassification rate of this matrix. Let's take a look at the output right here. I think it's that you guys can see that all very clearly, right? Good. It's just on, you know, in our classrooms, sometimes something low is not easy to see. So the misclassification of this matrix would be people who are blank, who are blank. Tell me one of the misclassifications. People who are predicted female, who are actually male. There's your 43 right there. And then the predicted male, who are actually female. This model does pretty well at what it does. So we can make the misclassification rate by 43 plus 36 divided by, that is the amount wrong we got out of that. But if we didn't have a model, if we did not have a model, and actually we could make this. Let me go back up to the LM right here. There it is. So if we did not have a model, I'm wondering if this will work. To kind of talk about not having a model, let's just put in gender 1, which should be the naive. It likes it. And now we visualize, it doesn't like it, but we give the coefficients, and actually the coefficient is negative, or the intercept is negative, which means everyone gets that answer. Everyone's negative 0.2. something we did not talk about is when we solve this, we solve it with e raised to the, which is exp here, e raised to the, and then we write our model, which is b0 plus b1x. And what is our model right now? Our model for this is just simply negative. Does that make sense? And then we do it over 1 plus e raised to the, which is exp in here. Does this make sense that I am solving for all people with the naive? And when I solve for all people with the naive, I get that. And if you remember going back in time, this model is the probability somebody is what? This model predicts the probability somebody is male. This is not the model, this is the naive model, and the naive model is a what? Flat line that predicts the, what's it going to predict? The probability somebody is male. It's not the mean, it's the proportion. And if you look, if I make a table right here, just to show it, table, old school commands, survey 10, gender, guess what happens when I make a table here? Oh wait, n rows, survey 10, that's what I want. What percent are male? Weird, I don't know why why'd the decimal accuracy go wrong? Because I didn't carry all digits, right? Just to show once and for all, I'm gonna copy this coefficient. It probably doesn't even have enough decimal places for me. But I hate when things aren't right exact, and still the decimal accuracy probably won't be enough to make it look perfect. But close enough, right? You see that the percentage of males in this data set is 44.77. What's the majority level? Female. So the model predicts all people are female, and it predicts the probability of male is just, well, 44.77% of those people are male, so what's the probability someone's male? Yeah, are we using any X's in the naive? All it knows is Y. Most people are female, someone's female. Someone's in Stat 201, this was Stat 201 data, they're probably what? Female, because most people are female. So that's our best guess. And when we do it via this matrix right here, here's what people forget, is you forget this data. That's just right here. These numbers, 386, 313. That's without your model. Still shaking? You can see this very clearly if I take off the n rows, and we just do this right here. Really? Same numbers. That's what those numbers are. That's without your model. Your model is the inside. Your model is making the prediction. This is just, there are 386 people who are actually female. There are 313 people who are actually male out of the 699. If you do the naive, that's the naive, which would predict all people are female, and it would get wrong everyone who is male. I do like one theory question. I don't know if I'll put this on the test. If you guys want, I will take this. If you're like, hey, Brian, you mentioned this during the review. This would be a great test question. I'll probably get a million emails about that. I'm still finalizing the test. I have to make 2 versions because you guys take them so far apart. And I basically wrote the comprehensive makeup 201 and the test 3. Woo, life's been busy. But with this in mind, a model that predicts, and we mentioned this in the Monday, Wednesday class, a model that predicts 100% wrong, is that at all useful? Why? What if you had a friend who every year, you've known him for 20 years, ever since a kid, he predicts the Super Bowl wrong every year? You could bring that friend to Vegas, right? Why? Because you know who's going to lose. He's like, I know they're going to win. I know it. I took Brian's stats class. Now watch out, that might change his abilities. It might be a change. But, or not, it might get worse. He's like, the Broncos are going to win. You're like, yeah, no. Not going to happen. Oh, wait. Oh, the Brown, right? That's who I was looking for. No, sports ball. Sports. With that in mind, I think this makes clear what the misclassification rate is. The naive model would be 313 over, am I putting this in the wrong spot? I should have done it elsewhere. The misclassification rate of the naive is 0.4477. That's got it. Any other big questions? I'll need to upload this. Hey. VIS, variance inflation factor. Yeah, we can throw that on. It's variance inflation factor is when variables in the model explain the same sources of variation. So we can actually check one of our multiple models here, like M3 for VIFs. So let's pull up M3 and run it for VIFs. This model actually comes back clean. It's using a different kind of formation of VIF, but obviously handedness explains about nothing, and weight explains about nothing. Do not worry that this is GVIF. It's still VIF. But I'm doing a categorical variable, so it has to use a different standard to do it. Still, the understanding of VIF is the variance inflation. Variance is very much like standard error. So variance is your lack of understanding, your uncertainty. If we inflate our uncertainty, is that a good thing? No. And variance is standard deviation squared. So if you take your variance inflation factor, it can give you an estimate of about how much you inflated your standard deviation, i.e., if we have a variance inflation factor of 16, our uncertainty, standard deviation, has probably increased by a factor of what? 16 for a reason. 4. The square variance is standard deviation squared. Variance square rooted is standard deviation. Now we are seeing standard error, virtually similar concepts. So we would have the standard error is probably going to increase by a factor of 4. 4 times more uncertainty, is that a good thing? No, usually we have a column of 5. But you do not want variance inflation, especially in a descriptive model, because the 3 things for a descriptive model, so things are going down right here at the end. The 3 things in a descriptive model. Task 1 is to find the right x's, and then give those x's the right. X's need what? Coefficients. Find the right x's. Give them the right coefficients, and then what those coefficients? Explain those coefficients. The descriptive model, you need to know what variables explain it. Then you need some coefficient for those variables, so we know, like 2 individuals who differ. And that's the explaining of that coefficient. When you give that explanation, you're literally telling me a variable, which is what you want for a reason. You're telling me the coefficient, and you're explaining it. You're doing the 3 things. Think about it. When I do the explanation, I can tell around the variable, the coefficient, and I'm explaining it. You're doing those 3 things. Pretty good model. Just do what? Predict. Let's see if we're going to pass go with that. Pretty good. And pass. If it works, it works. We'll see if the pretty good model works. So we'll stop at 1. We don't want that big of a. It's a training or a holdout. This is a holdout. But I tell you my model works, and we'll see how it works on new data. My model works as 100% success rate. So hopefully we haven't overestimated it. So how well does the model predict? We'll find out in the future. Any other last questions as we wrap up here? Good review tonight, guys. I'll put this under the review things. Also try to post the video. I hope, oh yeah, I did it via Zoom, so I get the link. So it'll be saved on my computer. Carolyn, let me give you this. Thank you very much. Thank you. I think mine's in my office. If it's not, I lost it. Hey, yo.
The syllabus for the,
yeah?
Are those the same as, because you said the syllabus was from last year. So are
the times are correct.
Okay, the times are correct.
So Monday, Wednesday, you have your exam. Friday at 8 a.m., right? Tuesday, Thursday, you have your exam Thursday. Is that correct?
Correct.
At 8 a.m. It's the 8 a.m. So Monday, Wednesday, Friday, I'm sorry. Why 8 a.m.? There should be donuts. Maybe 5 donuts tonight. I think it's 201 donuts. So I'm doing it with Missy. She has like 400 students. And I'm like, oh, don't want to buy donuts for 500 students. I'm like, I love my students. So I'm bringing M&M's to them, I think. Hey, bring it up here. I'm going to save this as we're talking. I'm going to choose encoding. That's fine. Documents. Review code. It's under documents. And let's go here. Look at that, it's so weird. And let's go to modules. Did you guys catch the hints on the take home throughout this? Did anyone catch any hints? Yes. Did it help?